for some reason. Seems like the...
Hello, can you hear me?
Now we hear you.
Okay. So thank you very much. I'm happy to give the last presentation here, and I have the advantage then that I can build on all these very nice presentations and the knowledge that you gain from them. And my name is Elias Ehrlich, and I'm working in the group of Robert Arlinghaus. And what I want to present today is a stakeholder-centered approach of management and modeling that we took for the BODDENHECHT project. And I'm responsible there for coordinating stakeholder workshops and the modeling part to provide forecasts on future management options. And if we talk about management, we talk about decisions. So you may decide once to invite some people and that you cook a nice goose. And then it turns out, okay, all the invited people are vegan. So you made a pretty bad decision and you had quite some effort and good intentions, but yeah, you may have asked them before. So from that example, you can see that stakeholder involvement could be actually quite important. And as we are close to lunch and everybody's hungry, I will not show you pictures of food anymore, but we will come to true fisheries management. And here, it's the same thing. So for successful fisheries management, there's the key element of cooperating with stakeholders. And only by that you can ensure biological, economical, and social sustainability. And there are different ways of stakeholder involvement. And yeah, the most minimal way is to not include them in the decision. So that would have, of course, some problems, probably with a lack of acceptability. Then you can consult them with some pre-selected options before the decision, or you can make some surveys with some management preferences. And if you have these surveys, then you can use these preferences for the evaluation of options. And there's the option to make a structured decision-making where the stakeholders are really a central part of. So we define the objectives, identify and evaluate management options. And here you have often a higher acceptance because it's more transparent. They can understand the decisions and they are more open to collaborate then. And that was the approach we want to take for the BODDENHECHT project, which is an transdisciplinary project. I think we have a lot about it. And it's about the brackish lagoons in northern Germany. And we heard that the pike biomass is currently declining and that there's an indication of slight grower overfishing. And it's co-exploited by recreational and commercial fishery. And recreational fishery is actually an important contributor to the harvest here. There are some discussions on what is the amount really. But what is really true, what we heard before from Robert, is that there are quite some conflict among user groups and that there's a discontent of stakeholders. So it seems that there is a need of change here. And that's our approach here. So we have an adaptive management approach with selected, with structured decision-making. And as you can see, we have a stakeholder group here in the center as they define the problem, identify objectives, and suggest management options. And then we provide estimates on outcomes of such management options based on a modeling approach. And also here they are included in building the model. So by that, they can evaluate the trade-offs and then they make decisions about management advices that will be handed over to ministry. The good thing is that the government really showed that they want to rely on the decisions of the group really, and that's a good motivation for the group. So this is the group. Dominique already said some things about it. So we have a good mixture here of different stakeholders. We have the scientist team and external neutral moderators, which are quite important for facilitation of the workshops. And we used these round tables for the discussion. And in last times it was often more a flat screen than a round table, but we managed in November to have a hybrid round tables with these recent pictures here taken from. So they had full consensus on the objectives. So they defined 7 objectives. One was increasing the pike stock, or at least maintain the current state. And increasing the catch rate, which is relevant for anglers, especially compared to the current state. And maintenance and facilitation of commercial and recreational fishery as coexisting cultural assets. And then there are further scientific and socially relevant objectives here. And then they identified several management options. So above around 50 management options, including habitat improvements, stocking, and as shown here, harvest regulations. And I will focus today here on the suggestions of reducing the back limits for anglers, which is currently 3 pike per day, and adapting the size limits. Currently, we have only a minimum length limit of 50 centimeters. How did we implement the model? So the idea was that the stakeholder actually first provide a mental model. So they have their practical knowledge and experience, which they put into a mental model. This process was led by us, so they can really understand how modeling is working. And based on their mental model, we built this mathematical model, and they suggested the measures to be tested with the model. And then we provided the modeling results. And here we have model output, which is related to their objectives. So we have some evaluation criteria. And by that, they can evaluate the success of measures and consider trade-offs. And we had the important function here to communicate the use and limits of the model, so uncertainties, and so on. So the mental model here, so it was about gathering the knowledge of stakeholders, and we restructured and subdivided it into 4 basic processes. And I want to focus here as an example on growth. And they managed to come up with a really complex mental model here. So they have quite some knowledge. And just to give you some examples, so here, for example, we have food availability, which of course has a positive effect on growth. And if you have a high pike stock, this may negatively affect food availability, and by that you have a density dependence on growth. So this is represented in this mental model. Or for example, here that you have males which have a lower growth potential than females, which is also included here. And then we made the transition to the mathematical model, and it was important to communicate that we really built on their mental model. And we used a sex-specific and density-dependent growth model here. So we included these links explicitly here. And then we parameterized these growth curves based on actual data from the lagoons. And having that, we had to communicate, okay, that we can't include all the factors. So we had to explain that modeling, it's about simplifying and focusing on the main factors, which are actually dynamic and affected by our decisions. And furthermore, we argued that by having the data from the lagoons, actually, we integrated several factors as they played a role when collecting the data. For example, if you have high food availability, the collected data would also reflect that. And this is then an overview on the model structure. So as you can see, it's an 8-structured sex-specific model with size and density-dependent processes. And we distinguished here between recreational and commercial fishery in link to the mortality. And for example, we have here a size-dependent fecundity relationship. So we have slight hyperaminometry assumed here based on indication from the data. Then we have this size-dependent mortality. So we have a high natural mortality at lower sizes. Then we account also for cannibalism, as we have this Rickert type recruitment function, where you have at a higher spawning stock biomass reduction of the number of recruits due to cannibalism, and further processes here. And then before we go into details on certain management options, I want to give you some general model insights so that you have a broader picture here. So what we can see here is the effect of fishing mortality. And currently we have a fishing mortality of 0.2. And then you can see here the yield in tons per year, the total amount and the amount of angler fisher. And you see that it is a scenario where we have dominance here of the anglers in relation to the removals. And in line with the stock assessment, the model predicts, okay, currently we are above the FMSY, so slightly growth overfished. And when we consider now the objectives, we introduced this traffic light system for the stakeholders so that they can easily get the main effect of the management option. So we have red for failure and green for objective achieved, and then one yellow one, which is close to the objective but failed. And now here's the spawning potential ratio. So what would happen if we decrease the fishing mortality? Of course, the spawning potential ratio would increase. So we are in the green area. For the fishermen, yeah, it's correlated with the yield, of course, the revenues here. And as we are currently about the FMSY, a slight decrease of fishing mortality wouldn't be a problem for them. And the same is here for catch per unit effort of the anglers. It's correlated with spawning, with the number of individuals here. And you can see it's going up if we decrease fishing mortality. And we considered also the number of caught trophy pikes here per angling day, and it's also going up. So in the current situation, we made clear decreasing the fishing mortality is actually beneficial to all defined objectives they defined. And actually, they could work together in the current situation. So that was what we tried to make clear during the workshop. And then we tested different management options. So one was reducing the back limit. And as I said before, currently we have a back limit of 3. And what you can see, if we first go to increasing the back limit, that actually it makes no difference of having a back limit of 10 or 3. So that means the current back limit is quite ineffective. And it would only have an effect if we decrease it to 2 or 1 or have full catch and release, what is equal to back limit of 0. And the same is true for revenue. Here we would have an increase for the fishermen, and catch per unit effort is also increasing if we have a lower back limit. And we made this clear by this green traffic light here. And the cool thing is actually that the model really is in line with data. So currently we have 2 pikes on average per angling day, which is in line with the data. And that is also why the reason why the current back limit of 3 is actually not effective. So only when decreasing the back limit to 2 or 1, we would see a positive effect on the objectives here. Okay, then another management strategy here is on the harvest slot. So what we can see here is the maximum length limit. So we have as a baseline the minimum length limit, and then we add maximum length limit. And the current situation is that there's no maximum length limit. So it's set here to the right side. Okay, thanks. And if we decrease the maximum length limit, we would have a positive effect here on the stock and a negative one on the revenue. So I have to say here that the harvest slot is in this scenario for both, so for fishermen and anglers. So that's why the revenues decrease here. But we would have a positive effect on the trophy catch rate and the general catch rate here. What we can see here is also that maximum length limit should be equal or below 90 centimeters. So otherwise it's not pretty effective if it's 1 meter or something. And we have a problem that we have some losses for the fishermen. Now a small overview, that was just a very small picture on the overall results. So the current back limit of 3 is not effective, so we should better decrease it based on the model results, and it would be positive in terms of all objectives. The only thing is maybe it's not quite accepted by consumption-oriented anglers, which are probably not only interested in catch rates here. Then we have the harvest lot for fishermen and anglers, which would have a disadvantage of loss of revenues, but we consider other scenarios where we have the harvest lot only for anglers, which wouldn't have this disadvantage, but of course, also the advantage according to the stock and the catch rate would be lower then. And this really depends, of course, on the scenario we consider regarding the amount of removals of fishermen and anglers. And the same pattern is true here for increasing the minimum length limit. If you would have, angler-specific treatment here with a size limit only for them or harvest slot, maybe there's the feeling of unequal treatment and the feeling of unfairness. This could be a problem here. Okay, but if we look at angler preferences, actually our model predictions or our model advices would be in line with what anglers prefer. So this is survey data from DITA. And you can see that their preferred back limit is between 1 and 2. If we would increase the minimum size limit, they would prefer 60 centimeter, and they would prefer a harvest slot if implemented of 60 to 90 centimeter, 85. Okay, and with that, I want to thank you all the working group members and the contributors. And I have to say that we were successful. We had full consensus on several measures of harvest regulations. And as a summary, so this stakeholder-centered approach was successful up to now for us. So we had consensus on definitions of problems and objectives. So we had really a common vision. We identified a broad range of management options, and the current state is that we have full consensus on first measures on monitoring and harvest regulations. And related to the participatory modeling approach, we can say that we are quite impressed by the complex knowledge of the system by the stakeholder group. And the mental model was quite useful in building the common system understanding and visualizing the model process. And we used it for the mathematical model as a basis. And we could really see during the discussions that they quite used the model results during the discussions and the evaluation process. And this traffic light system turned out to be quite helpful here. And the next step will be then including adaptive fishery behavior and spatial dynamics in the model to answer questions on what would be the effect of spatial harvest regulations like rotating closure, such things, and habitat improvement. Yes, and with that, I'd like to thank you for your attention, and also thank you for to the funders and collaborators. Yeah, and thank